All right, good afternoon, students. I welcome you back for another important and amazing session on atomic structure, students. The whole purpose is to help you understand the basic concepts of chemistry. You should be able to understand each and everything, learn each and everything that is important. Take chemistry as a science student. Chemistry is science to be learned, student, to be understood. Unless I will apply my mind, nothing will happen. Let me tell you, your mind is like a parachute. And if you don't open it, it will remain closed. And it doesn't work then. It does not work, student, then. Those who are diving from a height of 20,000 feet, students, they are coming with parachutes and they open it and then they land safely on the earth. Is it right or wrong?
Yes,
Tell me.
sir. Right.
If you will not open your parachute of the mind, it will be closed. And then what will happen? Nothing is learned. You will keep on interacting with the student. Energy level should be high when we take a class. Warm up session, energy level should be high. So we have already told you that the emission spectrum of hydrogen was the first one to be studied. Yes, and from that, what was the conclusion which was drawn from the emission spectrum of hydrogen atom? 30 seconds. Tell me what was the conclusion which was drawn from the emission spectrum of hydrogen atom, student. You are now talking with me, you are interacting with me. Before I start all this, I'm saying that the important point was the study of the emission spectrum of hydrogen atom. True. What was the result of that, student? What we obtained from this? Tell me, what was our result of the emission spectrum of hydrogen atom? The experimental evidence which was available, student. There were lines which were obtained in the case of the hydrogen atom. Lehman, Balmer, Paschen, Brackett, Stephen. Yes or no?
Yeah. Yes,
Okay.
sir.
Which line was in the visible part of the region? Which part, which line was in the visible region, students? All this you have to learn, student. You have already done it. You have to revise, keep on revising. That is what I say, student. You will forget everything. You are aware of which line are there in the visible part of the spectrum. Past 30 seconds only are given to students to warm up, students. You are aware of which series of lines were obtained in the visible part, student. They will be asking question: ultraviolet, visible, infrared. You have seen that. Balmer series.
Yes, sir.
Lehman series were in which region? Lehman series was in which region, student? Balmer scientist was observing the visible part of the spectrum. Then there were Lehman was in which series? Ultraviolet, visible, or infrared?
It was in well,
You have Lehman series, students. You are aware of all this. That's again, I say that you should be aware of each and everything now by this time, students, because you don't have that much time, students. Revising is very important. You will forget everything. Keep on revising, student. We are going ahead, and once we go ahead, you should be knowing what we have learned earlier. Otherwise, what will be the use of that? Tell me, students. What will be the use of that? So ultraviolet, you are aware of the ultraviolet region, you are aware of the infrared region, student, and how the lines were obtained, Lehman, Balmer, Paschen, Brackett. So you are aware of this. Lehman lines were observed in the ultraviolet region, UV. This was in the visible, and you obtained lines in the infrared and far infrared, student, also that was studied by Paschen, Brackett, and Piffen. The result of these was that there are, we said, energy levels in the atom. First approximation, there are energy levels, students. So we said that there are main energy levels in which the electrons are living inside the atom. That was the first approximation. True?
yeah.
The first approximation based on this data was that energy level. Which energy levels we talked of, student? N equal to 1, 2, 3, and 4, like this: K shell, L shell, M. So you said there are orbits in which the electrons are moving outside the nucleus, first shell, second, third. This was the first approximation. But students, when later on, what happened? When the emission hydrogen atom has got only one electron, students. When the emission spectrum of other atoms were experimentally found out. What was the result? For other atoms, when there were other atoms which have more than one electron, student, more than one electron,
Okay, sir.
and the ionization energies of these were determined. But they studied the ionization energies, student. What is an ionization energy, students? Energy required to remove an electron from a neutral gaseous atom. So they've tried to find out there's a limit of the, as you go to higher an ion energy, student, what we told you, there is a convergence limit, students. When further there is no change in the energy of the electron, students, and when we reach that limit, we say that okay, that is the point when electron is not inside the atom. That means electron has left the atom. That means ionization has taken place. That is the ionization energy, students. So what they decided is to find first ionization energy, second, third, fourth, like this. And these ionization energies were determined, student. This further gave, and the first approximation was then expanded, that each energy level in atom is made up of, what was the next thing, that each energy level in the atom, each energy level in the atom is made up of sub energy levels, is made up of, student, what is made up of sub energy levels. Okay,
Yes, sir.
there are sub energy levels, student, inside the energy levels in which the electrons will be obtained, students. Sub energy levels or sub shells, what do you call them? Sub shells, student. In the shells, these are the shells, student, K, L, M, N equal to 1, N equal to 2, N equal to 3, 4, 5. In them, you said there are sub shells, students, or sub levels. Which what sub levels you said ki there are in the K shell? You said there are 1s sub shells. Sub shell in the second main energy level is N equal to 1. In N equal to 2, you said L shell you have 2s and 2p sub shells, students. N equal,
Yes, sir.
you are having M, which is 3s, 3p, 3d sub levels, right? N equal to 4, KLM, N shell. These are the shells, and in the shells there are sub shells, students. Which one? 4s, 4p, 4d, 4f, and so on. True.
Yes,
So
sir.
there is a evidence, experimental evidence, which said ki first approximation that electrons are in the energy levels is not everything, student. In the shells there are sub shells, sub levels, and sub levels, students, are given as S, P, D, F. So the electrons are in them, and then we have told you that there are orbitals in which the electrons live, student, and maximum electrons that can live in one orbital is 2, right? Okay. And also, students, the ionization energies values were determined first, second, third, fourth, and so on for different elements. And the result was that the energies of the sublevels was in the order of, what was the energy of the sublevels? Energy of sublevels was in which order, student? S has
Okay.
lower energy than P, P has lower energy than D, and 4, F, right? Tell me, this is the order of the energies.
Yes,
Okay?
sir.
So the relative energies of the sub levels is given like this. Bolo, any doubt here?
No, sir.
That means experimental are going on. Emission spectra of hydrogen, then emission spectra of other atoms. They have more than one electron. Then determination of ionization energies, first, second, third. And on that conclusion, student, the result is there are energy levels. In the energy level, there are sub shells or sub energy levels, and then you have orbitals in the sub levels. These electrons are present in the orbitals. Orbital is the probability of finding the electron around the nucleus. Electrons are moving around the nucleus, students. It can never be inside the nucleus, that is clear. It is outside the nucleus at some distance from the nucleus. Electron is at some distance from the nucleus. ठीक है. And the energies, the lowest energy, you know, is the main energy level. If here is a diagram, student, here is a table to show what I said, that there is a main energy level. When the first, in the first energy level, there is only one sub level. In the main energy level, student, there is only first sub level. Which one? 1s. So tell me yes or no, fast. This is the first energy level which you are saying K shell. These are the shells, students, which we call as the first shell is K shell. It has only one sub level, which is 1s. The second one is L shell, or second energy level, has got how many sub levels? 2. So the number of sub levels is equal to the number of the shell. Third will have how many? 3 sub levels, 3s, 3p, and 3d. Okay. Fourth will have 4 sub levels, K, L, M, N shell. So these are the shells. These are our sub shells, students. Okay? Yes or no? Tell me.
Yes, sir.
And then you have said s orbital, p orbital, d orbital, f orbital, students. And the maximum number of electrons in each sublevel can be determined. Maximum electron in each orbital is 2. What is the maximum number of electrons in each orbital? 2, students. Yes or no?
2.
Fast.
Yes, sir.
So in S you can have maximum of 2 electrons. You can see S only 2. In P you can have maximum of 6 electrons. In D maximum 10 electrons. In F 14. Okay? Clear?
Yes, sir.
Because students, there is only one S orbital. And there are 3 P orbitals. There are 5 D orbitals. And there are how many? 7 F orbitals. This is known to us?
Yes, sir.
Okay. Note it down.
Yeah.
Okay, I will proceed further. I thank you very much that you are interacting with me, understand. Okay, students, that now there are energy levels, sub-energy levels, orbital students. And you know, we told you about quantum numbers also, students. How many
Yes, sir.
quantum numbers I told you, student? How many quantum numbers I told you? N, L, M, L, and MS. 4. Principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. 4 quantum numbers. Those quantum numbers derived from the Schrodinger's wave equation, mathematically. And using them, we can find out the number of what energy levels are there, what are the sub-levels and orbitals, and where the electrons will be present in the orbitals. 4 quantum numbers were used in the last lecture, yes or no?
Yes, sir.
And the energies can be determined, student, and we have used in building of the for the electron configuration, because our main objective is to write the full electron configuration. What is our main objective? To write the full electron configuration, student, of
Yes.
the different atoms. For atoms, we want to write the full electron configuration, or how will we write the full electron configuration of different atoms, students? Then there are certain rules which have been given. What are the rules which we used for writing the full electron configuration? Just tell me, students. I will give you 30 seconds. Answer the question. What are the rules which are used for writing the full electron configuration of atom? Which one? The first one? What was that? What are the principles which we use for writing the full electron configuration, student? Fast. You are getting 30 seconds to answer a question. You already know it. It has been done in the previous lecture. Which rule was used for the distribution of which we will, that level of the energy levels is given by whom in the building up of the process of electron configuration of different atoms? Tell me. Of Bohr.
Of Bohr's principle,
Of Bohr principle, student.
then Hund's rule,
Hund's rule. Third,
and the Pauli exclusion principle.
Pauli's exclusion principle. Students, we have already discussed these in the previous class, student. Pauli's exclusion principle. So these are the rules or principles, student, which are used for writing the different electron configuration. Although has given the various uh, that the first the electrons will go to the lowest energy level. What it says, electrons will first go to the lowest energy level, ठीक है, and then it will go upwards, ठीक है, then it will go upward, right? The lower energy is the most stable. So more stable means first the electron should fill the lower energy, then they will move to higher, because lowest energy means lowest potential energy, lowest potential energy. This is what, and then we told you, then what the Hans said, when you having the orbital, student, for example, you know that there is only one s orbital. S orbital only one, P3, D5, M, F, you are having 7. These orbitals are degenerate in a shell, students. They have the same energy in a shell, right? So what will happen if I say that I have one s orbital, student, I represent this by one box. This is an orbital, a way of representation. So if I say 2p, how do you represent 2p? Tell me. There are three 2p.
Yes, sir.
We represent by three. One is 2px, other is 2py, and 2pz, students. And when
Yes,
I
sir.
represented d, how many boxes I represented? How many orbitals? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. This was our 3D, 3D xy, 3D yz, students. 3D xz, and what you said, 3D x square minus y square and 3D z square. So these are degenerate, student. What do you mean by degenerate? What do you mean by degenerate? These are degenerate. Yes or no?
Yes,
Degenerate
sir.
is what I told you. They have the same energy. They have the same energy, and for F there will be 7 such orbitals. How many? 7. Yes. So when the electrons are filled, student, first they are filled with same spin. Only when they are filled completely, then the pairing starts. First they are filled. If there are 3 electrons, they go 1, 2, 3. After this is full, then the pairing starts. Right? That was the answer rule of maximum multiplicity, student. Right or
Yes,
wrong?
sir.
And first 1, 2, 3, 4, 5, and then pairing will start. So first the orbitals are singly occupied. After they are singly occupied completely, the pairing will start. That was the Hunt's rule. Because when they are singly occupied, student, then there is a lowering of energy. The pairing of energy will need some energy, student. When pairing takes place, energy will be required. So that becomes little higher in energy. The fourth was that the police said that electron has a spin. Electron has a spin, student. So in one orbital, the 2 electrons must be of opposite spins, right? So if I put one electron here, if I say this is my 1s, if this I show like this, then the other is of opposite spin, students. That was Pauli's exclusion principle. No 2 electrons can have all the 4 quantum numbers same, or in an orbital, no 2 electrons can have the same spin, students, in an orbital, right? So these are the rules which are being used for building or writing of the electronic configuration. You see that electron has a spin, student. Electron, this is my electron. This is spinning, student. It can spin clockwise, and it is like a small bar magnet. It is like a bar magnet, student. It is spinning, so it has a spin. If it is spinning clockwise, I am saying it has a spin of plus half. And what can happen? This electron can spin in anti-clockwise direction, student. Anti-clockwise, then this will become south, this will become north. So electron can be treated as a bar magnet, there's a magnetic field around the electron, student. So this will be my second spin quantum number minus half. Unpaired electrons, they are attracting, they have a magnetic field, student. They are paramagnetic. They will attract towards themselves, students. So because electron can be seen like a bar magnet, student. I've shown north and south, and here south and north. It is spinning around its axis in clockwise, student. It is spinning in anti-clockwise direction. That is why the spin magnetic quantum number was given based on the experimental data of the emission spectrums of different atoms. So students, all these four rules are important for writing the electronic configuration. In some cases, there could be few exceptions which will be discussed. In order to remember the energy level, students, that first which orbital comes, the lowest energy is first shell, second, third, and in the shells there are subshells, students, and in the subshell there are orbitals which are degenerate. So we can build up the full electron configuration by using this. So a diagram has been given to help the students to remember the order of the energies. What is this diagram here, student? देखो, I gave you last time also. You see one first the lowest energy is 1s, then 2s, 2p, 3, 1s, 2s, 2p, 3s, 4s, and you can have more, students. This you can see that there will be 5s, 5p, 5d, and 5f student. Then you can have 6s, 6p, 6d, and 6f, 7s, 7p, like this, students. What is the how it filled? It goes here 1s to 2s, 2s to 2p,
2p,
3s to
3s2,
3p,
3p.
4s to 3d.
Yes, sir.
This way, if I join these lines, this is giving me the order, students, order. So you can go further, students, like this, and you will join on the end. So this is the order of the energy, students, which will be filled. Now supposing question number one, you are said, I am saying, student, write the arrangement of electrons, write arrangement of electrons in, student, sodium atom. The atomic number of sodium is 11. Okay, I give you 1 minute to write it. Write down the electron configuration of sodium, students. You have 1 minute to answer the question. I will put my timer on. I will give you 1 minute. Okay, I have a timer, student. Timer.
Okay.
You will get 1 minute, student. This is my stopwatch.
1s2.
The stopwatch is on, student. You are getting 1 minute to answer the question, students. 1 minute to answer the question. Okay. Your time is up, students. Have you done it? Or I will do it.
Wait, sir, I'm doing it.
Doing
Okay,
it.
done it, sir. Done it.
Okay, tell me.
1s2, 2s2, and 2p3.
1s2, 2s2, and
2p3.
3. How 2p3? There are total of how many electrons? 11.
Okay, wait. That is for 11, right? 2p3, 3s2, and 3p1.
You can have how many electrons in P maximum?
You can have 3 electrons.
Who said 3? I gave you the information. Where is that? You have been given here also. See, S2, P6, D10,
Okay,
F14.
sorry.
We have repeatedly
6.
told you so many times. You see, there are 3 boxes for the P. In one, you
It'll
can
be
have
2p5, sorry. 2p5.
2p5. Then how many are 2 plus 2, 4, 5, 9 electrons?
4, 9, and then 2p6, and then 3s1.
1s2, 2s2, 2p6, and 3s1. See the order we have told you already. First, maximum electrons in S is 2. So 2, then 2, and maximum in 6, 6 in P. After that, how many? 11 is the atomic number. So students, what you get here, what you get? 1s2, 2s2, 2p6, 3s1. This is the electronic configuration of sodium, students. You should be knowing how many maximum electrons can be put. I have already told you. Any doubt is there? Any doubt is there? Now, if I say neon is a noble gas, tell me, noble gas. What is the atomic number of neon? 10. What are noble gases, students? Group 18 in the periodic table are noble gases. They have completely filled outermost shell. What is the electron distribution of neon? 1s2, 2s2, 2p6. This is your neon. Tell me, right or wrong?
Right, sir.
So here you have this structure. This is for sodium. Can you see this part? This is what? Neon. So you can also write this sodium student configuration. How? Neon is 10 atomic number. This is the noble gas 3s1. 3s. This is a short way of representing the electron configuration of sodium. Tell me, any doubt is there? Any
No,
doubt?
sir.
You could do it?
Yes.
Okay. Let me take some more examples before I do that. Students, I'm taking a slide which is free. Now I'm saying write the full electron configuration of iron. Fe, the atomic number of iron is, students, 26. Iron has got 26 atomic number. That means there are 26 electrons in the atom.
Of Fe26. That is 26, right?
Yes, atomic number 626 means 26 electrons are present in iron.
Yeah, yeah.
Sometimes, we know what type of energy level for iron. Energy levels, if we have to show n equal to 1, this is my K shell. This has got only one s orbital, students. This is my n equal to 2. This is my L shell, students. and it has got students 2s. After the 2s student, you have n equal to 2, and this is a shell, you have 2p. After 2p students, what you have?
3s.
N equal to 3 starts 3s. In the 3s students, then you have 3p, 3p. And then students, after 3p will come. After 3p students, what you have? 4s,
Yes, sir.
and then you have 4p. So you have 3p students, 4s, 4p. So you have to fill 26 electron students.
So it will be 1s2,
Two
2s2.
electrons here. Let me change the color. How many?
It will
Two,
be 1s2, then another two electrons,
two. How many?
then
First
6,
one, two, three, 4, 5, 6.
then
One, two,
another 2,
one, 2, 3, 4, 5, 6.
then another 2,
4s
4,
2.
4s2.
After 4s is student 3d. If you check it, how much? 4s 2.
Then 3d6.
3d 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. 3d 6. So that means students 1s2, 2s2, 2p6, 3s2, 3p, how much? 3p6, 4s2, 3d6. ठीक है?
Yes, sir.
26. You know, the noble gases, if I see what is the easiest way, what I will do, student, what noble gas is. You have helium, neon, argon, krypton, xenon, radon. Their outermost shell is completely filled. The atomic number is 2. Add plus 8, magic number 10. Add plus 8, 18. Add plus 18, 36. Add plus 18, how much? 54. Add 32, how much? 80. These are the atomic numbers. Noble gases, if we have to remember. These are called the magic number. Keep on adding, you will get the answer. Do you see how did I get the atomic numbers of these?
Can you
Now
explain
here,
again, sir?
from helium, I have gone to radon. These are noble gases, group 18.
Okay, yeah. So you just keep adding
8,
8,
8,
8,
18, 18,
18,
32.
18, 32.
Magic number addition.
So can I go to the washroom?
Okay. That means if I have write argon student, what is for argon? This is iron. What will be the electron distribution of argon? 1s2, 2s2, 2p6, 3s2, 3p6. This is our argon. 4 plus 2, 6, 6 plus 2, 8. How much is this? 1s2, 2s2, 4, 6, 8, and did I do it? 1s2, 2s2, 2p6. 2p6. 1s2, 2s2, 2p6, 3s2. This becomes how many electron? 4 plus 6, 10, 12, 18. This is 18. So I can consider this part, student. This is completely filled. I can say iron Argon I can write as 18, 4s2 3d6 students, 4s2 3d6. So this is the complete electron configuration of iron students, iron. ठीक है? Can you see what I have done, students?
Yes, sir.
Instead of writing the complete, I can write iron, which is the atomic number is 26 or 26 electrons like this. 18 argon is a noble gas, and then students 4s2 3d6, 4s2 3d6 students. Then I say write the electron configuration of germanium student, germanium Ge. Germanium atomic number is 32. So students, you are getting 1 minute to write the electron configuration of germanium. 32 electron students, 32.
One is two, two is two, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p2.
3d10. How many electrons? And 4p2. 4p2. ठीक है. So how many it becomes total? 32, 32 students. It is 32 germanium. It is in group 14 student, group 14 carbon silicon germanium, carbon silicon germanium. And if you write, see that this was how many? 32. How many electrons are there? 32 student, 32. And where is 32 less than this? If I use argon, argon is 18.
Yes, sir.
So if I say argon 18, where is argon 18? 2, 4, 4, 10, this whole. What is this? This is argon. Then what is left, students? What is left after the argon? 4s2, 3d10, and 4p2. Okay? This is another short form of writing the electron configuration, students. Electron configuration. You understood what I said? There will be some exceptions when we will write the electron configuration, student. There will be some exceptions to writing the electron configurations also. What exceptions are coming, students? For example, in the case of you will find that this is an alternate way of writing the electron configuration by using noble gases, by using the noble gases. ठीक है? Alternate way of writing the electron configuration. Another way we will tell you is by using the periodic table. Okay, let me go back. So here, student, I have periodic table. ठीक है? The periodic table, you see, this is the modern form of the periodic table. Yes? ठीक है? In this periodic table, students, you can see that this is my group 1. What is this? This which I am showing you. This is my, which one? These are the group number, student. This is my group 1. ठीक है? Group. And this is my group 2. ठीक है?
Yes, sir.
These are the 10 elements. This is what we say group 3. This will be group 3, group 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the group numbers. ठीक है? Group numbers. By red pen I am showing you. Can you see it? Group 1, group 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10. Then this is group 13. See, it is written group 13, 14, 15, 16, 17, and this last one, group 18. ठीक है? Can you see my red pen? Tell me. Red pen visible?
Yes, sir.
These are the group numbers. And let me
Okay.
see what are the period numbers. Period numbers, student. This is period 1. See, this is, in the period 1 you have hydrogen and helium.
Helium.
Period number 2, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. This is your period number 3, student. Period number 3, which is this sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Can you see it? This is my period number 4, students. In 4 you have potassium, calcium, and then there are scandium, titanium. These are called the transition elements. What are these transition elements? And then you are coming to gallium, germanium, arsenic, selenium, bromine, and krypton. So this, which period is this, students? Which period is this? 4th. 5th period, this is my 5th period. And the last one I have shown here is my 6th period. ठीक है?
Yes, sir.
So students, how many groups I have shown you? How many groups I have shown you? Tell me. Total groups, how many I have shown in this table? 18. How many? 1 to 18. ठीक है? Can you see 1 to 18 groups? Yes or no? Tell me.
Yes, sir.
How many periods I have shown here? How many periods I have shown? Tell me. 1 to 6. Can you see that? ठीक है? These groups are the vertical columns. What are these? In periodic table, we will, periodic classification, we will learn this again. Periodic columns. ठीक है? Vertical column. ठीक है? And in the period, student, these are the horizontal rows. ठीक है?
Yes, sir.
Rows. Total I have shown 6 horizontal rows and 18 columns. 18 columns, students. ठीक है? And you will see that those elements which are in the group, element which are in the same group, student, they have the same, if the elements in the same group have same outer shell electronic configuration, they have the same outer shell electronic configuration. Those elements which are in the same group, student, they have the same outer
Electronic
configuration.
configuration.
Which I am, for example, you take any group. Let me take, student, for example, group. I am taking group, supposing I take student, let me take, this is my group 15. ठीक है? Which group 15? This one?
Yes, sir.
Nitrogen, phosphorus, arsenic, antimony, and this is group 15. Okay? Can you see that group 15?
Yes, sir.
And in the group 15 student, what is their outermost electronic configuration? What is the outermost electronic configuration? Because these are the noble gases. After this, they are coming. The outermost electronic configuration is NS2 student NP3. That means 15 means 5, 10 plus 5. So 5 electrons are there in the outermost shell. 5 electrons are there in the outermost shell. Where students N, what is N? In this student, what is N? N is my period number. N is the student period number. N is a period number. For example, now let me take group 15. I am taking the group 15 configuration. I am taking student group 15. First element of group 15 is nitrogen.
Yes, sir.
What is the atomic number of nitrogen? 7. So what is the electron configuration? 1s2, 2s2, 2p3. Okay?
Yes, sir.
This is the noble gas, helium, atomic number 2. What is left? 2s2, 2p3. Okay? So n is here 2. N value here is 2. This I wrote general configuration for group 15. For group 15 student. This is the general electron outermost. So in the outermost you have 2s2, 2p2. And what is 2? This 2 is my period number. Period number is student 2. Therefore, student second period. Therefore, nitrogen is an element of the second period. And which group? Group 15. I can say that this nitrogen belongs to period number 2 and group 15. Okay? This is another way of simplifying the problem of writing the electronic configuration, students. The period number indicates the highest occupied main energy level. Period number, students, indicates what it indicates? Highest occupied main energy level. Main energy level, students. ठीक है? ठीक है? So when the outer electrons are being filled in p subshell, they are called p block elements. They are called p block elements. When the outer electrons are being filled in s subshell, they are called s block elements. And when the outer electrons are being filled in d subshell, students, they are called d block elements. And when the outer electrons are being filled in F block element, F subshells, they are called F block element. There are 4 blocks in the periodic table, which we will see in the periodic classification also. Therefore, student, group number, this is another way that we can simplify the writing of the electron configuration. For example, if I have to write the electron configuration of next element of group 15 phosphorus, I am saying write the electron configuration of phosphorus, students. I have written for nitrogen. Atomic number also I'll tell you, add 8 in 7. Add 8 in 7. What it will become? 15. See, I told you magic numbers to write this. Nitrogen, phosphorus, arsenic, antimony, bismuth. This is my group 15. Tell me. Yes?
Yes, sir.
So this atomic number 7, 7 plus 8 is 15. Okay? And if then you can add 18 in that, it will become 33. Add 18 in that, how much? 151. Add 32, then it will become how much? 32? 83. These are the atomic numbers now. Atomic number. What I did, add 8. Then what you added, student? 18 and 32. These are the magic numbers. By adding, I can get the number. So if I have to write the electron configuration of phosphorus, student, this belongs to group 15. And the general electronic configuration is ns2 np3, right? Outer electron configuration. What is that? Outer shell electron configuration. Outer shell electron configuration is how much, students? ns2 np3. Which period it belongs? What is the period in which the
NS2 and
phosphorus is present? Tell me. Third period.
yes, sir.
This is belonging to group 15, and period of this is
Period
which one?
3.
Third period. So the last will be 3s2 and 3p3. Last shell will be 3s2 3p3. N is 3 now. This was 2s2 2p3. This will be 3s2 3p. And then what I can write, which is a noble gas before that. This is my neon, student. Neon atomic number is 10. So what it becomes? The electron configuration is 10 neon. Neon is a noble gas, 3s2 3p3. This is the outer valence shell of the phosphorus, students. By this method also I can make and simplify the problem of writing the electron distribution. This n value, this is the last subshell, whatever is this value is the period number, students, is the period number. And you have 3 plus 2 5. In 5 if you add 10, student, that is my group number. So group, this is my group number, student. So what you do, student, group number is number of electrons in outer shell plus 10 in this p block elements, in the p block elements. In the p block elements, we can say that the group number will be equal to 10 plus number of electrons in number of electron, students, in where? 10 plus number of electrons in the outer shell. In the outer shell, students.
Okay, sir.
That will be our group number. That will be our group number. So this is the reason we have shown you this periodic table, that which is the group number, which is the period number. In the same group, the outermost electronic configuration is same. Can you see that? Same outer electronic configuration is there in the same group element. That is why these elements resemble in their properties also, students. We will see that in the periodic table, students. There are certain exceptions to what we have told you. We can work out the electron configuration, students, from the periodic table. So the p block is named because the highest occupied sublevel is a p sublevel. D is that because the highest occupied is the d subshell, student, with the electrons are being filled in the d subshell in the highest occupied orbital. In F, the outer electrons are being filled in the F subshell, so we call them F block elements. This is the way we write them, students. So there are certain exceptions also, student. These are the shapes of the S orbital. You see the S orbitals, shapes of these orbitals, student. This is the my shape of the S orbital. This is spherically symmetric. This, the more the density of this is giving you the probability of finding the electrons around the nucleus. Student, electron can never be inside the nucleus. It has to be at some distance from the nucleus. The more denser is the region, more is the probability of finding the electron. P orbitals are dumbbell shaped, student, and D orbital double and F are more complex. The shapes of these orbitals are derived by using the Schrodinger's wave equation mathematically. I'm saying. So you know there are 3 p orbitals. How many are there? If you have 3 axes, student, if you have 3 axes, then how many p orbitals are there? You are aware of that, student. There are 3 p orbitals. So if I say this is my x-axis, this is my y, and if this is my z-axis, you have, student, 3 p orbitals. If this is my 2px, then you have, student, 2p z, and then you have, students, 2py. There are three p orbitals, student, dumbbell shaped. They are degenerate in the sublevels we have shown you, and there are five d orbitals. There are five d orbitals, students. They can also be shown in this form. One of these has been shown here. These are there are five d orbitals. We can draw the shapes of that. You can see in different books, student. Dxy, dxz, dyz, dx square minus y square, and dz square. There are five d orbitals. They are degenerate. We show them by five boxes, for example. 1, 2, 3. As I in the box system, how do I show p orbital? I show you like this. S is only one. I show one box. This is my s orbital, student, and p. There, how many p are there? You are saying one is 2px, other is 2py, other is 2pz. There are 5d orbitals, these ones. So 3d, how many? 5. F will be, how many F are there? More complex than that. 7, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 7. So 4F, there will be 7 such orbitals. There will be, and their shapes are more complex. So you can see them. These shapes have been derived by using the Schrodinger's wave equation, students. Schrodinger's wave equation. So there are exceptions to writing the electron configuration. For example, student, for example, if I say we have to write the electronic configuration of student in the periodic table I have shown you, if we want to write the electronic configuration of chromium, student, chromium atomic number is 22, 20, 24, 24. So if I write it, you are saying argon is 18, and 4s to 20, and then it becomes 3d4. Okay, for chromium. But this is not the correct configuration of chromium. The actual configuration of chromium is not this one. Exceptions. I said there are exceptions to the electronic configuration, student. The configuration of chromium is 18 argon 4s1 3d5. It becomes, it changes in
No.
this. Why? Because
Yes, sir.
3D becomes half filled. Student, here half filled or completely filled, half filled or completely filled orbitals are more stable. Are more stable, student. Therefore, there are exceptions. Exceptions, I told you, there are exceptions. The configuration of chromium is not this, but it changes into this. Similarly, I will give you one more example, students. One more example. The configuration of copper. So configuration of copper, student, these are exceptions. Exception chromium, and I'm also giving another exception, 29 copper, student. These are exceptions, student, where half filled and completely filled orbitals become more stable. 29 will mean, student, if I write argon, what is argon? 18, 4s2 3d9. Okay, 4s2 3d1. But this is not the correct configuration. It becomes, student, what it becomes? 18 argon 4s1 3d10. This is the correct configuration of 29 copper. Again, I said half filled or completely filled orbitals are more stable. So what happens? One electron from S goes to D. These energy levels are not far away located. Their energy level gap is very small. So electrons can transform from S to D, students. And then this takes over the configuration 4s1 3d2. As I said, there will be exceptions to the electron configurations we are writing. So I hope you understood what I said. Is it clear?
Yes, sir.
All right, this ends my discussion on the electronic distribution and configuration, students, and we will give you more practice and see more questions in the next lectures. Meanwhile, you can practice and writing the electron configuration as per the questions given in your book. Okay, then I will meet you in my next class, students. Thank you very much. Bye-bye.
Bye bye, sir.